talk about Fukaya-Morse A infinity category.
Thank you very much. Thank you. Well, thanks very much to the organizers for the invitation again. So, yeah, so this is a work with Olga Chekeres, Andrei Losev, and Donald Humans, and here is kind of the detailed account on the archive with pictures and even pictures with colors. So I'll be this kind of talk that requires some color chalk. So so I should emphasize that kind of our inspiration here comes from ideas of Andrei Losev. So okay, so what I will be talking about is certain enumerative problem in Morse theory. Well, and whereas the topic of this week here is, well, supergeometry, or let's say supermanifolds. So how is that connected? So, okay, so one could say that, well, so how do we adapt this talk to the overarching topic of the week? So supermanifolds, well, kind of by refinement of structure, or by putting a special structure on supermanifolds, there is special kind of supermanifolds, the DG manifolds. Oops, when you have a differential on the sheaf of functions. And locally a DG manifold near the zero of the vector field that gives you the differential looks like an L-infinity algebra. So L-infinity algebras are a local picture or linearization, if you like. And there's a natural notion of push forwards for L-infinity algebras or homotopy transfers along deformation retractions. And there's kind of an analogous process for DG manifolds, sort of passage to a moduli space of a DG manifold. So there is some sort of a push forward procedure on both sides. So some kind of moduli space. And here it's a homotopy transfer of L-infinity algebras. And it turns out that this problem is linked to this homotopy transfer of L-infinity algebras in a very particular case, for very particular L-infinity algebra upstairs, very particular L-infinity algebra downstairs. I mean, there's a very simple one upstairs, and the one downstairs contains the answers to the enumerative problem. So the title of that paper is something like two field theoretic viewpoints on the Fukaya-Morse infinity category. So Fukaya-Morse infinity category is the name for an algebraic package that contains the answers to this problem. And one of the field theoretic viewpoints is sort of a field theoretic rethinking of this process, where you think of it as the process of inducing an effective action on slow fields. You have some sort of gauge theory that depends on some, with action depending on some field, and then you split fields into slow and fast ones, you integrate out the fast ones. And the effective action on the slow fields is inducing the effective action on the slow fields in the sense of Wilson's effective action is this process. So, okay, so that was kind of the forward. The plan is that I'll first talk about the structure. So I'll talk about Fukaya-Morse A infinity category, which I'll call F. So in its original form that was proposed by Fukaya in 93, and also plus some kind of enhancement that we are selling in this paper. So a very natural enhancement. So and then, well, the kind of viewpoint, I don't know, 2A is in terms of homotopy transfer of infinity algebras. Well, more naturally, homotopy transfer of A infinity algebras rather than L infinity. So it's better to talk in associative language rather than Lie language. And sort of the field theoretic rethinking as a effective action. The effective BV action. For some gauge theory, some very natural topological gauge theory upstairs, and downstairs you get sort of some generating function for this data. And this will be a kind of a computation of an effective action by Feynman diagrams, and somehow, well, in a special gauge, which is kind of at the core of the matter here, in a special gauge fixing. And in this gauge fixing, kind of the very nice thing is that Feynman diagrams are literally the objects we are counting here, the Morse trees that I'll talk about in a second. Usually Feynman diagrams are something complicated, like some integrals over configuration spaces of points. Here, this is just a counting problem. So this is in kind of in physics language, this will be a second quantization viewpoint. There's also a first quantization viewpoint, which I'll talk about briefly. First quantization viewpoint, which goes by the name, well, I will follow Andrei's preferred terminology, higher topological quantum mechanics. So it's kind of a toy version of TCFT, topological conformal field theory, so in dimension 1 rather than 2. So you'll obtain, instead of obtaining kind of differential form on the moduli of curves, on the moduli space of curves, here you're obtaining a differential form on the moduli space of metric trees. Okay, so here I'll be kind of brief in that point. All right, so Fukaya-Morse infinity category, not a very standard name, but there was a paper in '93 of Fukaya where he proposed sort of both the what is usually called Fukaya category these days, one attached to a symplectic manifold and Lagrangians in it, and also its Morse counterpart. So he proposed both versions there. So let's fix a Riemannian manifold. Riemannian manifold. And okay, so let me describe the data of this A infinity category. So the objects, so there will be some finite set of objects, and objects are just functions on M. So I just select several functions. And I want them to be, well, sufficiently generic, so functions in general position. In particular, I want pairwise differences to be Morse functions. So, and a single object is a single function from this list. So there are n objects. So smooth functions in particular. So now morphisms between two functions. So I want that to be, Morse cochains of the difference Fa minus Fb. So in particular, what it is it is a span over integers of critical points of Fa minus Fb. So Fa minus Fb, by this genericity assumption, is a Morse function. So I look at the critical points. So and then I consider sums of critical points with integer coefficients. So here, everything is graded by Morse co-index. So the number of positive eigenvalues of the Hessian at a critical point. So more usually one talks about Morse chains, and everything is graded by Morse index, the number of negative eigenvalues. Here, I want the cohomological convention. Okay, and there's a differential here, which is, well, the Morse differential, which counts the number of rigid gradient trajectories connecting a critical point of some Morse co-index K and critical point with one higher Morse co-index. Okay, so now what about compositions? Well, this is kind of the meat of the story, compositions. So here I should say, well, higher compositions, so compositions and higher compositions, and D-Morse is actually an example of a composition, but so usual compositions are 2-to-1, higher compositions are 3-to-1, 4-to-1, and so on, so eating several morphisms and spitting out a single morphism, and there's also kind of a lower composition that takes a single morphism and spits out a new morphism, and that's this one. So the compositions are like that. So if I have a sequence of objects of some length, and then I have some morphism from here to here, some morphism from here to here, some morphism from here to here, so a composable sequence of morphisms. So then I need to tell you what is the composition here. And I will give it in terms of generators. So if I put a single critical point here and just extend by z linearity to all Morse cochains. So I put some critical point, and let me denote a critical point of the difference fa0 minus fa1, capital P, well, a0, a1. And then some other critical point of the difference of fa2 minus fa1, so pa1, a2, sorry, of fa1 minus fa2, and so on, pa k minus 1, ak. So these are just some critical points of the corresponding differences. So then let me just write it like that. So the composition, so I'm composing these morphisms, right? So the composition of these morphisms is, so let me say it's like kth composition because it eats k morphisms. So the composition is a sum over critical points of fa0 minus fak. So P ranges in critical points of fa0 minus fak. Some integer, let me denote it like that. So it counts the number of points of some moduli space times, well, the corresponding generator, pa0 ak. So what is this thing? What is this number? So it is some integer. So so this M is the space parameterizing certain pictures. What kind of pictures? So it depends, and it depends on this choice of critical points. So I have my point. Let me just give it in some example. Let's say that k is equal to 3 in this example. So I have some critical point pa0 a1, and then from it, so this will be a picture inside X. Inside X. Oh, sorry, I called it M there. Let me call it X. I think. Let me call it X rather. I'm sorry. Let's call it X. So inside my Riemannian manifold, I have a critical point. Then I consider a gradient trajectory of the function fa0 minus fa1. So I take minus the gradient of this function, and I consider the trajectory of that vector field. And then I also have my other critical point, pa1, a2. So a critical point of fa1 minus fa2. And from it, I look at some gradient trajectory of fa1 minus fa2. Then, well, I'm interested in the situation where they meet at some point. And from this point, I want to emit a gradient trajectory of fa0 minus fa2. And let's say I also have pa1, a3 in the game, and I'm emitting some, let me put some orientations here. I'm emitting a gradient trajectory of fa1, sorry, a2, a3. So I'm emitting a gradient trajectory of fa2 minus fa3. They meet someplace. And from it, I emit a gradient trajectory of fa0 minus fa3 until I reach my prescribed critical point of fa0 minus fa3. So this is a G embedded in X. right? So it's some kind of rigid picture inside the Riemannian manifold. And here I can sort of just for combinatorial reasons to like account of various decorations, it's nice to think of it as a ribbon graph. So to put sort of borders here, so imagine that there's actually a very thin ribbon around it. So, and put the decoration A0 here, A1 here. Oh, this is, okay. This is very, okay. This is supposed to be green. A2 here, and some other color, A3 here. Okay, so we're counting pictures of this type. So the space of such pictures with prescribed critical points, so let me call it M, space of such pictures. So if my functions are sufficiently generic, this will be a smooth manifold of certain dimension, and well, it's easy to write down the formula. It's, okay, it's minus the sum of co-indices, Morse co-indices of the kind of incoming critical points, plus Morse co-index of the of this outgoing critical point, and some shifts by k minus 2, where k is the total number of colors involved. So okay, it has some dimension. So, and here, if it has some non-zero dimension, then, well, this coefficient, we say that it is 0. If M is a zero-dimensional moduli space, then we are just counting the number of such rigid configurations, the number of such rigid trees. So it's just a count of points or count of Morse trees. And when this dimension is 0, then they are kind of undeformable, right? So there are no continuous moduli. So count of Morse trees. Well, more precisely, actually, this M is, so everything should be equipped with orientations here, and this is something that I would like to sweep under the carpet, but M is actually oriented space, and this should be an oriented count. So some points will be contributing with +1, some points with -1. Okay. So this is the construction. So the compositions are in terms of counts of such pictures, counts of Morse trees. So the theorem is that, and this is Fukaya, and well, more details in a later paper by Fukaya and O, is that, well, that the structure relations of an A infinity category hold here. So the A infinity relations hold. Okay, so let me just remind what are the A infinity relations. So if I have some sequence of composable morphisms, let me call them now x1, x2, and so on, xk. Each of them is a combination of critical points. Then I can sort of select some substring here and compose it, and then compose so replace the substring with its composition, and then apply the composition to the resulting string. And a sum over the ways to select the substring is 0. Again, with appropriate signs, and let me just not worry about signs. So the relations are that sum over ways to select the beginning and an end of a substring. So for any kind of inputs, R plus S plus 1 dot x k, that's 0. Well, actually, there are some signs, but let me not worry about them. So, okay. Now, one remark is that this infinity category is directly related to the maybe more famous or more studied Fukaya infinity category, which particularly is kind of gained traction in relation to homological mirror symmetry. So the Fukaya category of a symplectic manifold. So, namely, one has the Fukaya category of one can consider the Fukaya category of the symplectic manifold, which is the cotangent bundle of X. So here the objects are Lagrangians, but let me select special Lagrangians. Let me select the Lagrangians LA, so one per each function there, which is the graph. So it's an exact Lagrangian. It's a graph of the derivative of the function f there. Yes, please.
So when you in this in this infinity relation, you can have a substring that's just one item, right?
Yes, and you absolutely, yeah. There are such terms here. Mm-hmm. Yeah. And you can. There are also terms where first I select the entire substring and then I hit the result with mu1. Mm-hmm. So yeah, and let me sort of put kind of sneakily some parameter here, like small parameter epsilon, which I will then be sending to 0. So yeah, so these are, so I think I should think of epsilon as being small. So somehow in this cotangent bundle, I'm looking at sort of Lagrangians that are in some sense close to the 0 section, right, for epsilon small. So they kind of lie flatly, almost flatly there. So then kind of the morphisms in this Fukaya category, they're, well, given by Lagrangian Floer homology. So, but they're spanned in particular, so it's Floer cochains of a pair of Lagrangians, but in particular, it's a span of intersection points. Now, it's interesting that if you look at intersection points of two such Lagrangians, then you see that as such an intersection point projects to a point which is a critical point of Fa minus Fb, right? So if they intersect, that means that d of Fa minus Fb at some point is 0. That means that my point is a critical point of Fa minus Fb. So such critical points actually project to the ones that were morphisms in that picture. So, and compositions, they come from the count of pseudo-holomorphic disks. Well, let me cut out the pseudo-holomorphic disks. Actually pseudo-holomorphic. So, and what kind of disks? So I have, I don't know, like, let's say, I want to compose, I have L1, L2, and L3, let's say. So this is L1, no, this is L2, so I have some intersection point of L1 and L2, and then I have an intersection point of L2 and L3. And I want to compose them, so the composition will be in terms of, it's a linear combination of intersection points of L1 and L3. And the, so I think, so this is a picture of Lagrangians inside T star X. And the coefficient of that critical point, of that intersection point, is the number of maps of holomorphic maps of a disk into this picture, so that kind of arcs on the disk follow the appropriate Lagrangians. So they give you paths on the appropriate Lagrangians. So we are counting holomorphic maps from a disk to this picture, so that the arcs on the disk follow the corresponding Lagrangians. So, okay, so this is kind of this well-known Fukaya category. And the interesting thing is that if you project this picture onto the base of T star X, you will have some sort of amoeba between the critical points. And if you consider the limit epsilon to 0, then this amoeba becomes very, very thin. And in the limit, it approaches a Morse tree. So in the limit, we are counting the same pictures if we project from the cotangent. Yes, please. Yes, that's a good question, but I don't have an answer ready. So. Yeah, absolutely, absolutely. Yes. Sorry, I think I thought about this question, but I forgot the answer. So, no, but yeah, I need to think. yeah, so you're somehow, you could say that you are somehow rescaling the moment. No, but yeah, no, I don't have a meaningful comment. Sorry. So, yeah. Okay. So, yeah, you want to say that you are somehow zooming out, but yeah, I don't know how to say it correctly. Zooming out of the amoeba. So, okay, so the kind of there are a bunch of problems with this category. So, well, one could say that it's a partial category. This category that I formulated here. Maybe before saying that, okay. Well, it's partial because, for instance, it's not clear what are the morphisms from an object to itself, right? So, because the difference of fa and fa is 0. It's not a Morse function. So you need to do something else here. So before going there, just a little remark that, well, one might be interested what type of topological information Fukaya category remembers about the manifold, the underlying manifold X. So of course, each morphism space itself as a complex remembers, for instance, the cohomology of X, just because it's quasi-isomorphic to cohomology. But if you have this Fukaya category data, then Fukaya-Morse category data, then you remember more. And in fact, you can recover, if you have sufficiently many functions, then you can recover Massey operations on cohomology. And for instance, for X, a simply connected manifold, you can recover its rational homotopy type from Fukaya category, from Fukaya-Morse category. But probably there's more topological information there. So most likely there's more because there's some extra integrality data. But I cannot actually say how much more. So, okay. Now, enhancement. Well, that's just a suggestion of what to use for endomorphisms. So for endomorphisms of an object, so for morphisms of an object and itself, let's use smooth singular chains of X. It doesn't actually depend on this function. Let's just use chains. So, and then the one-to-one composition, so I need to sort of extend the definition of compositions to this case. So the one-to-one composition, I want it to be just the geometrical boundary operator. Now the two-to-one composition that eats two chains and spits out a single chain, I want it to be just the geometric intersection. And higher compositions will be 0 if the inputs are just chains like that. But then I need to say what are the compositions of more complicated sequences of morphisms that are not just sitting at the same object. And here, let me just give it in an example. So the idea is that now we will be counting Morse trees subject to an extra condition that they pass through given chains. So for instance, if I have, I don't know, a sequence like that, FA naught to FA1 to FA1 to FA2. And so here I have some critical point, PA naught A1. Here I have some critical point, PA1 A2. And here I'm sitting on the same function, so I should take some chain. So let me call it Z, or if I want to remember sort of its color, then maybe I put this color as some subscript, or even ZA1 A1, because it goes from A1 to A1. So, okay, now such a composition would be the following. So I would be summing over critical points of FA0 minus FA2. Okay, so this generator times an integer. So what's the integer? So the integer is the number of, well, certain pictures in X. So what are the pictures in X that we are counting? Okay, so PA0 A1, so I have some gradient trajectory going from here. PA1 A2, gradient trajectory going from here. They meet someplace, and they go to A0, A2. And I want to count such Morse trees that, now let me actually put some decorations here with, I mean, to put colors. So this will be A0. This will be, oh, this is a strange color. Okay, A1, and this will be A2. So I'm counting such pictures, so I have a chain of color A1. So I want then I have some chain in my manifold, ZA1, and I want my Morse trees to intersect it somewhere along one of the strands which have A1 as a part of their bicolor. So either on this strand or on this strand. So that's the rule. I'm counting such Morse trees, subject to the extra condition that they intersect this chain. So I could have sort of more chains in the game. So I could have, let's say, I don't know, 2 consecutive chains here, and then ZA1, 1, and then ZA1, 2. And then I would ask that as I go counterclockwise here, I first encounter ZA1, 1, and then I encounter ZA1, 2. I could, of course, have also chains with other colors and then more conditions on my Morse tree. So this is some sort of an more elaborate counting problem, more elaborate enumerative problem. So the statement is that still the A infinity relations hold. Then there are different ways to prove it. And well, essentially, there's a way through homotopy transfer of infinity algebras, which is what I'll explain in a moment. And then there's its sort of physicsy counterpart, effective BV actions, where the A infinity relations, they correspond to the Batarin-Vilkarisky master equation, that the Poisson bracket of effective action with itself is 0. And there is kind of an interesting way through higher topological quantum mechanics, where one has sort of the argument mirrors the argument how one proves WDVV equations from sort of looking at the differential form on the moduli space of curves, and sort of you use the fact that it factorizes on nodal curves. So there's a similar argument there. So using the kind of the Stokes theorem on the moduli space, not of curves in this situation, but of metric trees. Okay, but sorry, could you say?
The second FA1,
Mm-hmm.
put a small contribution to it.
Yes.
So then you have a kind of the usual composition law that you use.
Yes, if I replace it with some function that's maybe close, but still the difference is Morse, then I would put critical points there.
Right, so you get the usual picture of composition, and then you try to send the derivation to 0.
Right.
That picture kind of degenerates into this current picture.
Good question. I don't know. So I think the general expectation is that, well, what you should have is a sort of Morse bot chain. So you should have kind of differential forms on the critical locus of the difference. So here the difference has sort of a critical locus which is just isolated points. Here it's maximally degenerate critical locus. But yeah, so this limiting process that you're talking about, so yeah, it's a good question, but again, I cannot answer. So it's yeah, so it should in some sense converge to it, but I don't know how. So well, I guess if you sort of want to collapse everything into some sort of cohomology, then so yeah. You need to sort of, yeah, to set up the problem, you need to probably first go to somehow project from Morse cochains to, I don't know, cohomology of X, and then you can ask this question whether there is convergence there. So at this level, I'm not even sure what the question means. So, okay. So, all right. Now, I wanted just to give a small taste of what A-infinity relations look like in a simple example. So this is, I think, when you talk about Morse theory, there are a few standard examples. This is one of them. It's, but I don't know. I call it heart-shaped sphere, but I don't know if it's a standard name. So here the manifold is S2. There are only two functions in the game. And we are actually only interested in their difference, F1 minus F2. So, and I'm imagining that my sphere is embedded into R3, so that kind of the function is the sort of the vertical coordinate of the embedding. And well, it's embedded as this shape. So then there are 4 critical points of this third coordinate. So let me call them P, Q, R, S. So let's say that I want also to fix a chain. And my chain would look like this. It will be, this is my chain. So, okay, then let's say that I want to apply my infinity relation to the following sequence. So as a morphism from F1 to F2, I take this critical point, P, and as a morphism from F2 to F2, I take the chain Z. So let's see what's the corresponding infinity relation. So, so I can hit P with composition, and then compose with the chain. I can hit Z with composition, and then evaluate the composition of everything. Or I can hit everything with composition, PZ, and then hit it with composition again. And the infinity relation tells me that this is 0. So we can actually see what these terms mean individually here. So for instance, if I hit P with composition, here it's just Morse differential. So the Morse differential of P is, well, there are only there's a single rigid gradient trajectory going from P, and it ends in R. So this is R. Now, okay, now I need the exterior composition. So I compose R with Z. So so I'm counting rigid gradient trajectories starting from R and passing through Z. So there are 2 rigid gradient trajectories from R. They both end up in S, and one goes on our side of this part, and the other on the opposite side. But only the one on the other side, on our side, passes through Z. Only this one. So this is +1 times the endpoint S. Okay, so this term is S. Now this term, let's say that this is oriented like that, and I have 2 endpoints, A and B. So this is just the boundary of Z, so it's A minus B, this part. Now, I'm looking at rigid gradient trajectories from, let's say, first from P through A to wherever. Actually, there are no gradient trajectories from P through A. All gradient trajectories from P, they're restricted to the left side of the heart. So there are no gradient trajectories through A. But there is a single gradient trajectory through B, and it ends up in S. It goes like that. And so this is S, and well, with minus sign because of the boundary, because of orientations. Okay, now what about the last thing? So the inner composition, so compose P with this chain. Well, here I have actually a one-dimensional moduli space of gradient trajectories from P that pass through Z. So I have a lot of trajectories here that go like that. So this is a one-dimensional moduli space. So then I say that this composition is 0. Okay, so the relation is S minus S is 0, so it is indeed true. So generally, these infinity relations, for more general situations, they give you some interesting relations between the answers to the enumerative problem. Another example, or class of examples. So okay. So another example, so again, let me take only two sort of objects in the game, or two colors. So I have some manifold X, not necessarily a sphere. And let me fix, okay, so first of all, I have, again, two functions, and I'm only interested in their difference. So let me enumerate the critical points. Let's Pi are the critical points of F. So I have some critical points, I have enumerated them. Let me also say that I fixed some collection of cycles on my manifold, some collection of cycles. Let's say finite collection of cycles. Okay, so now what I want to do is construct the following matrix. So it will be of the size, the number of critical points by the number of critical points. So a square matrix. So its ijth element will be the following. It's the sum over sequences of cycles, so n tuples of cycles. Now I'm counting the number of gradient trajectories that are emitted from a critical point Pi to Pj and pass through some cycles C alpha 1 C alpha n and end up, and we should end up in Pj. So C alpha 1 C alpha n. So this corresponds to looking at the composition, for instance, like that. From F1 to F2, I take Pi, then I take C alpha 1 to F2, and so on, C alpha n to F2. And well, I'm thinking about this higher composition, and I'm taking the coefficient of the result, coefficient of the critical point Pj. So this is this number. So, and let me just construct a generating function for these numbers. So let me multiply it by some generating parameters. So I have one generating parameter for each element of this set of cycles, and they are either even or odd, so they are commuting or anti-commuting. So, and the rule is that, well, I can actually assign z degrees to them, and the z degree is to do 1 minus codimension of the cycle. So, okay. So this is some sort of enhancement of Morse differential. So we are counting not just gradient trajectories, but gradient trajectories subject to condition of passing through a bunch of cycles. So, okay. Now a lemma here is that this is indeed a deformation of the Morse differential. So if I define a new differential as usual Morse differential plus this matrix that I constructed. So this acts on what? It acts on Morse cochains of F tensored with, where I extend the scalars by my generating parameters. So, okay. So what's the lemma? The lemma is that it squares to 0. So there are different ways to prove it. So way one is it's actually a direct consequence of A infinity relations for this type of compositions. So way two is the following. Let's see. Okay, maybe I erase this. So way 2 is from homological perturbation lemma or homological perturbation theory. And it goes like that. So if I look at the complex of differential forms on X, on one side, and on the other side, Morse cochains of my function. So, okay, upstairs, this is a complex with de Rham differential. Downstairs, it's a complex with, so here I secretly tensored it with reals on downstairs because I want sort of to have analysis. I want de Rham complex upstairs. So let me, okay, with real coefficients. Okay. Right. So I have Morse differential downstairs. Now, there is a way how you can see Morse cochains as a direct summoned inside differential forms. So this was discussed in particular in the paper of Kantsevich and Soibelman from 2000. And they also actually discussed this Fukaya-Morse category in that paper. So there is a way to include Morse cochains, project from differential forms to Morse cochains, and find a chain homotopy between the identity on differential forms and projection followed by inclusion. I'll write these formulas in a moment. So, but the point is that, yeah, you can include, you can essentially split differential forms as the image of Morse cochains there, plus some acyclic complement. And then, okay, then the idea is that we are now in the setup of homological perturbation theory. We can consider deformation of the differential upstairs. Let me write it in some other color. So I want to add, it's very fragile. Okay, so I want to add upstairs a correction to the differential. I want to perturb it by the following differential. So this is a delta form on my cycles multiplied by the generating parameter. So here I'm a little bit sloppy with analysis. So if you want really to stay in smooth differential forms, you need to regularize and then sort of lift this regularization. This is possible to do consistently. One can have sort of a good smearing procedure here. So, okay. So this is a version of Novikov differential where you are deforming the Rham differential by by adding to it a wedge with a closed one form. Here it's not a one form, here it's like differential forms of different degrees, but sort of multiplied by parameters that carry some degree. Yes, that's the idea. Yes. But well, here we want to have a connection. Well, yes, that's what we are doing. But we are doing it, yes, at the level of cochains, so you want some kind of smeared delta form. Yes, right. Yes, that's correct. So, okay, then homological perturbation theory tells you that, well, you have deformed the differential upstairs. It still squares to 0. And you will have some induced deformation of the differential downstairs. So this induced deformation, so let me call this thing delta. So it's a perturbation of the differential upstairs. So the formula from homological perturbation theory is like that. So so what I should write here is I should go upstairs, do the deformation, go downstairs. And then there's a correction. I go upstairs, do the deformation, do the perturbation of the differential, then apply K, do the delta, and then go downstairs. And then a term with 2 Ks, with 3 Ks, and so on. So it's a geometric progression formula. So, okay, so this is formula from homological perturbation theory. And it tells you that automatically the whole thing squares to 0. But then you can compare to what we wrote there, and actually this term is when we intersect with a single cycle. This term is where we intersect with 2 cycles. Well, okay, given the appropriate I, P, and K, which I didn't write for you yet, but I'll write in a second. So this term will be the intersection with single cycle, 2 cycles, 3 cycles, and so on. So actually, this whole thing is exactly this M of t. I'll tell a little bit. Yeah. So I'll tell you. So okay. So actually, what are the time restrictions? So.
10 minutes official.
Okay, I see. Okay, so I should maybe speed up a little bit. So okay, so but this maps here are kind of important. So I is the map that takes a critical point to the delta form of the unstable manifold of P. So that's everything that can be reached from P by following the flow, the gradient flow. So the map P, it takes a differential form to a sum over critical points, that critical point times the integral of your form over the stable manifold. And K, somehow the most important object here, so that's a integral operator from differential forms to differential forms, 1 degree lower. And well, I can write it as integral over the proper time of contraction with the gradient vector field, and then pull back by the flow in time t of the gradient vector field in time minus t. Or in other words, it has an integral kernel which is distributional. So this is an integral operator with distributional kernel, which is given by a delta distribution on a submanifold Y. So its integral kernel is a delta distribution on a submanifold Y inside X cross X. And this is a submanifold given by pairs X comma Y, such that I can reach X from Y by following the gradient flow in positive time. X is flow in some positive time applied to Y.
What does MT square to 0?
Sorry?
MT, does it square to 0?
Yes. Sorry, no, it doesn't square to 0, but the sum squares to 0.
I see. So that satisfies the marker.
Yes, exactly. Yes, you could have defined M differently so as to include this term by kind of asking that there are 0 cycles there. So here I'm starting the sum from n equal to 1. I could have started the sum from n equal to 0, and then I would have included this term. So, but anyway, yes. So the equation is that this whole object squares to 0. Okay. Now, okay. So. Okay, so there are kind of two approaches that are mirroring one another. So kind of math and physics to this what's going on. So kind of the math one is that you have differential forms tensored with matrices of size n by n. So and that object has a structure of a differential graded algebra coming from the Ram differential. And the product comes from wedge product here and usual product of matrices. So our elements here are just, n by n matrices, where I have, at each slot I have differential forms. So, okay. And now I have downstairs, I have an object, let me call it M. So it's a direct sum of M, A, B, where A and B go from 1 to n. Where MAB is on kind of 4 diagonal entries, this is just differential forms. For the off-diagonal entries, these are Morse cochains. Okay, so you can think here that I have matrices where at the diagonal terms I still have differential forms as above. And for the off-diagonal terms, I have some, so differential forms, and for the off-diagonal terms, I have Morse code chains, so some finite dimensional vector spaces. So same as above on the diagonal, off-diagonal, something small. So I have inclusion, projection, and chain contraction here, which are trivial on the diagonal, because on the diagonal nothing changes. And off the diagonal, they are given by this data applied to the FA minus FB. So, and then I can induce from this DGA structure, differential graded algebra, an A infinity structure downstairs. And this is done by as a sum of the sum over trees, sum over binary rooted trees. So if I have a bunch of elements in this M, so I have a sum over binary rooted trees. Okay, just some example of a tree. So, and I put the inclusion of my objects downstairs on the leaves of the tree. At each vertex, I calculate the product upstairs. At each edge, I calculate the K underline, and when I reach the output, I apply P underline. So this is some sort of an iterated operation that eats several inputs in M and produces an output in M. So this gives me a polylinear operation on M, which, so this is a form, an application of a Kontsevich-Soibelman sum over trees formula, and it satisfies A infinity relations. So we are producing this way polylinear operations on M, which endowed with the structure of an A infinity algebra. Structure on M. So in fact, moreover, these operations, they satisfy certain selection rule. So they are only non-zero if this x1 is, so I should think of this A and B here as sort of the source and target object and sort of elements. So this is kind of a repackaging of the data of the Fukaya-Morse category. So A and B correspond to the object, and the element in the matrix corresponds to a morphism. So I want x1 to be from some color A0 to A1, x2 A1, x2 to the next color, and so on. So I want this sort of selection rule that the output of x1 is the input of x2, and so on. Only under this selection rule, these trees will be non-zero. This corresponds to the fact that there is sort of a secret ribbon structure here, that I should put A0, A1, and so on. Okay, so this is kind of the data of the Fukaya-Morse category packaged as an A infinity algebra. And here we are obtaining it from the sum over trees Kontsevich-Soibelman formula. Now, the physics viewpoint on it is that it's very natural. Okay, there are two physics viewpoints, but okay, so one viewpoint is that you're looking at a topological gauge theory, which is the BF theory. So your action is the integral over x of B dA plus half A bracket A. So the fields are non-homogeneous differential forms with coefficients in matrices. So A and B are both in differential forms on X, tensored with matrices. And similarly for B, with appropriate shifts, so by 1 and by n minus 2. So n is the dimension of the manifold. So, okay. Now, what are we doing? The idea is we want to integrate out the off-diagonal components, to integrate out the off-diagonal components of the fields A and B. So they have components like there's A, AB, and B, AB. So we want to integrate out the off-diagonal components or integrate them out almost completely. So inducing certain effective action on the diagonal part and the remnants, let me put it like that, remnants of the off-diagonal parts. So this is a topological gauge theory. So when doing that, you need to impose a gauge. So at the heart of the matter is a gauge fixing.
Why do you need generic n-bind matrices? You have to pick up some Lie algebra or whatever.
Here I really want n-bind matrices. Here I really want n-bind matrices for comparison with Fukaya-Morse category. So these actually correspond to target source and target objects.
So what's your Lie algebra GLN?
Well, okay, let me put it like that. Here I was actually sweeping something under the carpet, so I need to tensor it with some auxiliary algebra, which I will take to be upper triangular matrices of some other large size and twiddle, and the Lie algebra is this product. So I take the product of this associative algebra and this associative algebra, and then I skew-symmetrize it to a Lie algebra. That's the Lie algebra. Yes, but I have to do that because I want to recover a very particular data.
But would you know how to do perturbation theory if it's not something semi-simple with pairing and stuff like this?
No problem.
No problem.
Here, absolutely no problem. Yeah. Mm-hmm. So I don't actually use the killing form anywhere. This is sorry. No, here I should put for B I should put the dual, but yeah, actually there's no problem here. So at the heart of the matter is the gauge fixing, and the gauge fixing is it's a version of axial gauge that. And it's the axial gauge which points in different directions for different components of fields. So I want that the contraction with the gradient vector field for Fa minus Fb for a bth component of the field A is 0. This is for A different from B. And similarly for the B field. So this is some sort of a weird gauge fixing, which is a variant of axial gauge, but sort of instead of the axis, you have sort of directions of gradient vector fields, and they're different for different components of the gauge field. So then what you do is somehow, okay, how to say this? Well, you have a big space of fields, and I think of it as, okay, pairs of A, B, and I think of B as a cotangent coordinate, so it's T star minus 1 of essentially differential forms, tensored with matrices, and tensored with this auxiliary algebra. And then it's fibered over slow fields. So actually, I'm splitting it as slow fields and fast fields. So slow fields will be cotangent bundle of this M that I introduced over there. Well, actually, tensored with this auxiliary algebra. And fast fields are the, well, appropriate complement. So I'm thinking of F as fibered over F prime with sort of copies of F double prime placed over different points of F prime. So these are my fast fields. So, and I want to do the fiber integral. So I want to integrate the exponential of my action, where I represent the fields A as, well, A slow plus A fast, and I integrate over A fast, but actually over a Lagrangian inside A fast, inside the fast fields. So this Lagrangian is a very particular Lagrangian, actually, given by, defined in terms of my operator K that I introduced there, and, oh, okay, sorry. So the Lagrangian is defined in terms of this chain contraction K. So, all right. No, this will not work. Okay. Okay. So it's essentially image of K plus for the A field plus image of K for the B field. That's what essentially it is. So in the result, I want to call it the exponential of S effective of A slow, comma B slow. So then this is an integral, it's a perturbed Gaussian integral. That's easy to calculate. It actually has only 3 diagrams contributing to it. So you have S effective of A slow and B slow is the sum over trees, but here they are non-planar trees, so up to isomorphisms, trees up to isomorphisms. And then I'm summing certain expressions corresponding to these trees, so the inclusion of the slow field into all fields. So I put K on each edge. I put the bracket upstairs in the big complex, and I pair with the slow B field using the projection. So this is a sum, and here is 1 over the number of automorphisms of a tree. So it's a sum over non-planar trees without planar structure. So I can think of the result as a sum over B prime and some polylinear operation applied to A prime. So this way I'm producing, some skew-symmetric polylinear operations on M tensored with my auxiliary algebra to the power n. Well, actually, wedge power n, to M tensored with the auxiliary algebra. So, okay. So the point is that, theorem, this is an L infinity algebra downstairs. So L infinity rather than A infinity. So from physics perspective, this is the equation that S effective, with S effective, the Poisson bracket is 0, or the BV bracket. So this is somehow a property of a gauge theory, the Batarin-Vilkavisky-Master equation. So here there are only tree graphs, so that there's no sort of H bar components to think about. So L infinity relations come from this equation, and my Feynman diagrams, actually, if I analyze them in terms of what K is, they are exactly counting the Morse trees. So in fact, S effective is the generating function for the data of Fukaya-Morse category. So I can recover, in particular, those higher multiplications that I constructed here from the effective action, from this L infinity data. So how to pass from the L infinity data to A infinity data? I should just apply my operations to some appropriate elements. So I should take my elements in M. Oh, I did it again. Let me just do it like that. So I should tensor them with some elements of my auxiliary algebra, which are just matrices which have zeros everywhere and 1 at a single spot. So elementary matrices. So this one has 1 here, the next one has 1 in the next slot, and so on. So applying L to such a sequence of elements, I obtain Mn of x1 dot xn, tensor the matrix which has, 1 elsewhere and zeros everywhere else. So I can recover the data of an L infinity, of A infinity algebra from this family of L infinity algebras. That's why I needed this auxiliary algebra lambda. So there is something sort of funny going on here, and that sort of, for our enumerative problem, we were interested in A infinity algebra that encodes the A infinity category. When we need to go to physics, somehow physics in the sense of B formalism cares about L infinity structures, not A infinity. So we needed to somehow repackage everything into Lie data. And so that we don't lose information through skew symmetrization, we needed to tensor it with an auxiliary algebra. Then from this family of L infinity algebras, we still remember the A infinity algebra we were interested in.
So what's the dependence on lambda?
Right. So, okay, so my fields, they take, so they are differential forms with values in matrices tensored with lambda. So, so I need to prescribe some, I don't know, some critical point and an element of lambda here. So I'm constructing an L-infinity algebra on this bigger space. If I tried to remove lambda from here, I would have constructed some L-infinity algebra. But it would be a skew symmetrization of A-infinity algebra I was originally interested in. So we would have lost a part of the data, a part of operations we were interested in. So what I'm trying to say is that there is an A-infinity structure on M. And by skew symmetrization of it, well, we have some L-infinity structure on M, but it is forgetting. This arrow is forgetting. So this is a skew symmetrization arrow. So the way not to forget anything is to first tensor it with lambda, which has just associative algebra. Then you produce an L-infinity structure on M cross lambda, tensor lambda, and then this family remembers the original A-infinity data. So the skew symmetrization of this family of A-infinity algebras remembers the original A-infinity data here. And moreover, to recover, I don't know, n-to-1 operation, you need lambda to be a skew symmetric matrices of sufficiently large size, at least n by n. Otherwise, you will lose that data. So that's sort of the comment on A-infinity versus L-infinity here. So I'm out of time. So so I explained the sort of the second quantization viewpoint. So for the first quantization viewpoint, I can try to summarize it in, I don't know, like 1 minute, or maybe I should not do it. Let me not do it. I will just yes. Let me stop here. Thank you. Yes, please.
Well, to me, it all sounds what your written was doing 30 years ago when you take a cotangent bundle of S3 and it's related to variable calculations and large n expansion, large n sum, so you translate. And it seems to me that you are trying to do some version of tropical limiting to the same type of calculations.
That may be.
A priori physicists will come and say just re-expand you want for large n, for example. That should be good.
Right, this is not Chern-Simons. This is easier somehow, right? This is BF.
Of course, but the whole idea that you can try to check, gauge theory for counting polymorphic maps, that's basically a general idea. And we do it in different ways.
Well, I guess you're right. So yeah, that
So
makes sense.
You are doing some degeneration of
Yes.
story.
That sounds about right. And actually, this was a side project from something that was actually about counting sort of tropical maps. But here, instead of tropical, there is this, well, Morse, but they behave in a very similar way. And let's see, the main point of interest for us here was somehow this gauge fixing, this sort of axial-like gauge fixing. Yeah, this one. This was somehow the key formula for us. So yeah, that's, yeah. No, but I agree. It looks like a tropical limit of counting holomorphic disks, or tropical, I guess, in some sense. Okay, this epsilon sense that I talked about in the beginning.
This epsilon, there is no trace of this epsilon in this story.
No, epsilon is already 0 in this story. Mm-hmm. I guess epsilon is sort of the distance, sort of, I don't know, from string theory to field theory.